Let's work now on problems from Siegel's biochemical calculations. Now we are going to do problems on page 45. And we're going to start with problem 45. So again, in Siegel, problem number 45. This segment here we're going to do part A. And again, this is in page 93. So it asks here in this part A of the problem, what's the pH of a solution, a 1 millimolar solution of alanine hydrochloride. Alanine hydrochloride. So the major challenge for the students is to know which form is the amino acid in this particular problem. So first one that comes is alanine hydrochloride. So if you search, for example, alanine hydrochloride in PubChem, for example, you are going to get that the formula is H2N CH dot HCl. So that's the form of hydrochlorate, amine hydrochloride. So it's not very informative this way that is displayed here for us to solve the problem. But that's a very common way of displaying the form for medicine. Lots of medicines are weak acid or weak base, and they treated those bases in particular with hydrochloric acid. And in the drugs, you are going to see the name of the drug followed by hydrochloride. That means it's protonated. So what we need to know is what version of this alanine we are dealing with. So what we have in reality is the protonated form of alanine, which is Ala plus. So this alanine with the form here Ala plus, when you put this in water, what's going to happen is it's going to deprotonate. The carboxylic group here obviously is the first one to deprotonate, and it's going to generate H3N CHCOO minus. So basically what they're doing is that we're bringing to equilibrium two forms of alanine, the alanine that was initially the alanine plus, now in equilibrium with alanine 0 plus a proton, right? Normally you don't need to write the proton, but this particular problem we want to know the pH, so we need to know where's the concentration of protons and so on and so forth. So for solving the problem, first we need to know the Ka. The Ka we are going to find here in Siegel in the page 409. Could use another table. There is the appendix 7. That you can find all this relevant information, and obviously in an exam you are going to be provided with that information, right? So in this place here, the Ka1 with the K for the carboxylic group is 4.47. 10 to the power of negative 3. It's a very large Ka, because as you know, the pKa for carboxylic group is very small. So it's a strong acid, basically, stronger acid than acetic acid, for example. So what we have to do now is to calculate the pH of the solution based on this Ka that we have here. So let's scroll up a little bit here, get a little bit more space for us to work on this problem. So we have an equilibrium between alanine plus and alanine 0 with the protons, and initially we had a concentration of 10 to minus 3, and the part of it deprotonate, dissociate, and it's going to generate X and X. So in the equilibrium, we are going to have 10 to minus 3 minus X of alanine plus, X of alanine 0, and the X concentration of protons. So all we have to do here is to determine the concentration of H plus and then we would have the pH. So from this we know also that Ka is going to be equals x times x divided by 10 to the power of negative 3 minus x. Let's plug in the numbers and calculate. This is going to lead us to a quadratic equation that we have to deal with that. All right, so then we have now Ka is 4.47, 10 to the power of negative 3 equals x squared over 10 negative 3 minus x. So from here we have x squared. Now I'm going to multiply this term by this 1. So it's going to give me 447 10 to minus 3 times 10 to minus 3 minus from this second term here 447 10 negative 3 times x. I put all the terms in the similar place and get a little bit more room for writing. So we're going to have the all terms together. We're going to have x squared plus 447 10 to minus 3x minus 447 10 to minus 6 now. 10 to minus 3 times 10 to minus 3. So 10 to minus 6 equals 0. So this we can solve by using the quadratic equation, and we know that this is the Bhaskara form that all very known to us. So we plug in these numbers and then we get x equals minus 447 10 to minus 3 plus or minus, it's going to be a long term here, 447 10 to minus 3 squared minus 4, a is 1 and the b a and the c. Now c is minus 447 10 to minus to the negative 6, and all of these divided by 2a, a is 1. So we have then x equals minus 447 10 to the negative 3 plus minus, let's see what we get from this negative there in the negative, so it's going to become positive for 47 exponential minus 6 and 447 10 to minus 3 squared, and sum it up, it gives us 0.00615. Now we have 0.00615 minus 447 exponential 3, change sign, 0.00168, and divide this thing by 2. It's going to give us 0, 3 zeros after the comma, 84 molar. This is the concentration of protons. So if the concentration of protons is like that, the pH is going to be minus log of that number, which gives 3.07576. So let's say 3.08. It's a good approximation. So that's how we find the solution. And obviously we know that in our exams we tend to avoid quadratic equations. So the problems are normally with x very small. However, this one in particular, we can't get around it. We have to solve it to the quadratic equation. Because the pKa is so small, if you approximate that and neglect the x term, it's a big error that we have in the calculation at the end.